Hello, I am Reetam Chattopadhyay. This is assignment for mechanism sessional sheet 5. We have chosen the topic windscreen wiper mechanism. This report is collectively presented by Reetam Chattopadhyay, Soumyadeep Das and Arnab Mondal. The report contents are as following: problem statement, displacement analysis, velocity analysis, acceleration analysis, force analysis and velocity simulation, acceleration simulation, force simulation and at last the innovative idea. The problem statement is synthesize and make a simulator for the windscreen wiper mechanism. After the analysis part, we will be covering the simulation parts in MATLAB. So now, let's start with the displacement analysis of the mechanism. The displacement analysis gives the relation between the input angle theta 2 and output angle theta 4. Here we take AB equal to L2, BC equal to L3, CD equal to L4, DA equal to L1 as the link length AD being fixed. DE equal to L0 is an extension of link CD which connect the mechanism to the wiper. The mechanism can be visualized as a simplified form as shown on the top. Taking the origin as A, we can easily calculate the coordinate of point B and point C. And as BC is equal to L3, we can find the distance as shown in the calculation. Here, coordinate of B is L2 cos theta 2, L2 sin theta 2, and coordinate of C is L1 plus L4 cos theta 4, L4 sin theta 4, and we can find L3 by distance formula. And the obtained equation can be simplified as A sin theta 4 plus B cos theta 4 equal to C, where A is equal to sin theta 2, B is equals to cos theta 2 minus L1 by L2, and C is equals to L1 square plus L2 square plus L4 square minus L3 square whole divided by L1 L4 into 2 minus L1 by L4 cos theta 2. Now, by using the half angle formula, we can put x in place of tan theta 4 by 2, so that sin theta 4 will be 2x by 1 plus x square, cos theta 4 will be 1 minus x square by 1 plus x square. We can obtain a quadratic equation of x as written here. We can obtain the value of theta 4 from here, and after that we can also obtain theta 3 from the bottom formula. Velocity analysis provides relation between input angular velocity theta 2 and output angular velocity theta 4 dot. From Aronhold-Kennedy theorem, three bodies that are in relative motion must have collinear instantaneous centers. From that, I24 must lie on I23 I34 means BC, and also on I12 I41 means AD. So it will lie on the intersection of BC and AD. So now we can find the length of EA and ED, where E is the intersection of BC and AD. Now from the concept of instantaneous center, we can find the relation between theta 2 dot and theta 4 dot, where theta 4 dot is the Jacobian of theta 2 dot.
Acceleration analysis gives the relation between the input and output angular acceleration. From the velocity analysis, we have theta 4 dot equal to j theta 2 dot. Now differentiating with respect to time, we get theta 4 double dot equal to j dot into theta 2 dot plus j into theta 2 double dot. Now theta 4 double dot equal to partial differentiation of j into theta 2 dot plus j into theta 2 double dot, and we can calculate the equations further. The torque analysis gives us the relation between input and output torque. Now del W1 plus del W0 equal to 0 equal to tau 1 del theta 2 plus tau 2 del theta 4 equal to 0. So tau 2 equal to minus tau 1 into del theta 2 by del theta 4 equal to minus tau 1 into theta 2 dot by theta 4 dot equal to minus j inverse tau 1. Here tau 1 equal to input torque, tau 2 equal to output torque, and j equal to Jacobian obtained from velocity analysis.
Now let's see the MATLAB simulation along with the code explanation. In this snippet of code, L1, L2, L3, L0 represent the link lengths. We are considering friction force To make the mechanism as real as possible, we are also considering a time interval of 0 to 7 with increment of 0.05. The point A and D are fixed, and as explained in the displacement analysis, we can find all the points. We are using theta 2 to explain theta 4. From this, we can find coordinates of all the points and lengths of all the links. In this code, to find the velocity of E, we use the internal function of MATLAB to differentiate. This is the code, and this is the code for the torque velocity relation, and this is the code for the acceleration. This is the loop starting from t0 to 7, and at each increment of 0.05 it makes the mechanism with all its link parts and all its component and delete it after interval of 0.05. But to find the shaded area, we specifically did not delete the wiper length, which will be more clear after simulation. So let's wait. So in the simulation, we can clearly see the area shaded, and we also can observe the velocity versus time graph. Now let's see the acceleration simulation of the wiper mechanism. The highlighted portion of the code is the main part of the acceleration simulation. Here, j theta 2 is the partial differentiation of j with respect to theta 2, and similarly, j theta 4 is the partial differentiation of j with respect to theta 4, where j is Jacobian obtained from the velocity analysis. Now we can run the code. Here we can see the shaded portion, and I can also observe the acceleration versus time graph. Now let's see the torque simulation. The highlighted portion of this code shows the relation between the output torque and the input velocity. Now let us run the code. As from the code, it is torque versus time graph. We can observe it, and we can also see the shaded area. We can draw an interesting idea about the wiper mechanism. As we know, the purpose of a wiper is to clean the area of the screen, but due to its mechanism, it can only wipe a circular area. After much of a discussion, we came to a conclusion that if we can use an actuator as a wiper, we can change its length, thereby increasing the area of wiping.